works. All right. Yeah. First topic, limits of two growth functions. The question, how do we describe limits of two growth functions? Basically, the ratio of two growth functions. Yeah. We calculate the limit when the problem size n goes to infinity. Yeah. When we do that, so here we consider the general case, very abstract case. When we use the limit to compare two growth functions, how many cases do we have? We want to look at all the possible cases. The limit value, all the possible cases. Yeah. So let us recall, use your calculus background. Yeah. When you do this, how many possibilities do we have? Yeah. So let me list all the cases. Yeah. You can see, basically we have four cases. We try to cover all the possibilities, four cases. The first, limit equals 0. Yeah. That's simple. Second, C, non-zero constant. C, it's a non-zero constant, so I put a C. Okay. Third, infinity. Infinity. The last one, other than these three, we still have another case. Other, what's that other? Yeah. Yeah. The limit does not exist. How do you know the limit exists, right? Nobody can guarantee that. Sometimes the limit does not exist. Yeah. Sometimes you may ask, I cannot imagine the situation when the limit does not exist. The limit does not exist. Well, I cannot imagine. Okay? Yeah. Yeah. Here, I may like to give you a simple example. The limit does not exist. All right. Yeah, let me just change the color. All right. First, let me just show a simple sequence. Limit does not exist. 1, -1, 1, -1 to the infinity. This pattern repeats to infinity. There is no limit for this one. Okay? No convergence, right? Up and down, never converges to one fixed number, not 0, and it's not infinity. Not the first case, not the second case, not the third case, other. All right? Does not exist. Four cases. All right. So now, let us look at all these cases and try to put the categories, try to create categories for these cases. Yeah. So let us do simple discussion. The first case. All right, so here, look at this ratio of two growth functions, f of n, g of n. So we compare which one grows faster, all right? Slower, yeah. So to talk about that, we use a terminology, order of growth. Yeah. The f function grows with certain order. So we call it order of growth. Yeah. For example, square order, for example, right? Cube order, fourth degree, right? So that kind of order. Logarithm, right? Logarithm also order of growth. So things like that. So we use this concept, order of growth. So basically, when we calculate the limit of the ratio of these two functions, we compare their order of growth. We do the comparison. Which one has larger order of growth? That means that function grows faster. All right, so for the first case, you can see the ratio goes to 0. That means the denominator function grows faster. Yeah. Because eventually, when the problem size is really large, the limit goes to 0. The ratio goes to 0. Yeah. 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 So the computation, you see the result. Yeah. Yeah. So that one we can easily see order of growth of f of n less than order of growth of g of n. Yeah. That's the case 1. Yeah. Then for other cases, let's look at other cases. All right. Case number 2, constant c, non-zero constant c. Okay. Yeah. Yeah. Let me put the, yeah. Since I put it here, let me just write non-zero constant for our algorithm problem. We should put greater than 0. All right. Yeah. But look at that. The reason. In our algorithm context, we do not consider ratio negative constant. The reason is very simple. Efficiency number, basically the number of operations, right? Yeah. F of n, g of n, we use them to represent number of basic operations. That number, how can you make it negative, right? Yeah. So that's why I say in math, we allow C negative, right? In math, if we just talk about, general math, then C could be negative. But in our algorithm context, we don't have that meaning, right? Not meaningful. Yeah. All right, so here I put greater than 0. Now positive constant. Yeah, we just say positive constant. All right. So then, for the case number 2, if the ratio, the limit is a positive constant, no matter what the number is, 0.1, 0.00001, it doesn't matter. The value of C doesn't matter. We will say these two functions have the same order of growth. Yeah, even extremely small number, yeah, because based on our intuition, we feel, f of n over g of n, the limit equals 10 to the negative 7th power. Very small. We like to say, g function has higher order of growth than f of n, but based on our definition, it's not. Okay? The constant. The positive constant, its value is not important. Remember, you may ask me why. Remember the last time when we do the ratio, f of 2n over f of n. Remember the last time, let me put it here. We look at f of 2n over f of n. We look at this ratio, the constant cancel out, right? The constant cancel out. Yeah. So that's why we only care that constant is non-zero. Other than that, the value after cancellation, not important. Yeah. All right. So I hope you understand this case number 2. Same order, okay? Order of growth. Yeah. Then case number 3, you can see f of n. Yeah, because infinity, the ratio goes, when n goes to infinity, this limit is infinity. Yeah, so you can see, naturally, you can understand f of n grows much faster, right? Infinity, right? So we can say order of growth of f of n greater than order of growth g of n. Yeah, that's the first 3 cases. How about number 4? Now we are at the number 4 case, other. Yes, other. Right. Number 4, the limit does not exist. If we do the limit calculation, we have to stop somewhere. After we detect there is something wrong, we have to stop the calculation. It does not exist. So then, the limit calculation method will give us problem. We have to consider different method. Yes, we have to consider a different method in that situation. Okay, yes, all right. So we need a new method for case number 4. New, non-limit method. Yeah, let's say non-limit method. We have to change the course. That happens frequently in the real world. When we try to solve a real world problem by a special method, if we get stuck, when we get stuck, we have to change our method. Use a different method. Yeah. Here, that's the case, so we need a new method to solve the problem. Okay, all right. Yeah. All right. Objective for, yeah. Now, for this new method, all right. So here, look at our situation right now. We want to compare order of growth. And we assume the ratio of their limit does not exist. Yeah. Here, we need a special method to help us still find the answer about the comparison result of their order of growth. Yeah. All right. Yeah, so that's the goal. That's what we are going to do. Yeah, later we have that method. Yeah. All right. So let's put it on hold a little bit. All right. Yeah. So we will answer this question, yeah, later at some time. Yeah. So let us go to another question. Yeah. We need some notations to represent these, let's say, 3 cases. Yeah, because this one, we need to answer it later. Yeah. The answer still not easy to see at this point. Yeah. So let us look at the first 3 cases. Yeah. First 3 cases, we want to find some compact notations. Yeah. Why? The reason is because if we want to talk about these 3 cases, do we want to say words long, relatively long, right? So we don't want to say every time we say, a lot of words. Yeah, not a very efficient, right? So in this situation, we like to introduce some new notations. When we use those new notations, we do not need to say a lot of words. We just apply the notations. Then people in this field can understand immediately. What's the meaning? All right. Yeah. The first notation, when the order of growth of f of n less than order of growth g of n, we say f of n belongs to little o. Look at this symbol, little o of g of n function. So what's the meaning little o? Just notation. Okay? The meaning means this limit of the ratio equals 0. That's why. But it's not 0, it's a little o. Yes, we use the little o. Yeah. In math, notation is very important. Good notations can make our thinking much better. Notation help our thinking. Yeah. Little o notation. So this one, the first one. Yeah. The meaning, yeah. So you should go back to the limit case and order of growth case. Yeah. In your mind, yeah, you have that information. Number 2, big theta. Big theta, when they have the same order of growth, we write this notation. F of n belongs to big theta of g of n function. Yeah. So that means their limit when n goes to infinity, positive constant, and they have the same order of growth. That kind of meaning. All right. The third case, little omega. Little omega. All right? Yeah. order of growth greater than of Fn, greater than g of n, we use little omega. Okay? Yeah, pretty abstract. Pretty abstract. Yeah. All right. Here, so let me explain a little more about these three notations. Yeah. And we do a little more understanding on these three notations. All right. These three are our most important three asymptotic notation. We call asymptotic notations. Yeah. Yeah. Approximate. Yeah. Not very precise. Asymptotic. Yeah. And we have more actually. Yeah. Later when we have chance, we may go to a few more, but these three, the most important three. Yeah. Other cases we rarely use. Yeah. Sometimes we may use a little bit. Yeah. For example, little o, so we have big O notation, right? Big O notation. Yeah. Little, big theta, we have little theta notation, right? Yeah. Little omega, we have big omega notation. Yeah, so you can see, another three, the meaning just the opposite. Yeah, but we rarely use them, so I may not go there. Yeah, only when I use one particular notation, then I explain the meaning there. Yeah, all right. So that's one explanation. Another one. Yeah, another one. This notation, when we use math understanding here, f of n is a function. In math, what do you mean f of n belongs to? Belongs to this little o of g of n. What is the mathematical object here? Right? In math, we may like to understand really precise the meaning for each notation. Mathematical object, what is that, right? Yeah. Here, this object in math, it's a set concept. In math, you know the set concept, right? Yeah. So that one is a set. Set concept, okay? Yeah. So this is an element, right? F of n, a function. We treat that function is an element in the set. So this notation belongs to or is contained in the set. An element in the set. That's the meaning. Okay? Yeah. So later you will see, when you see asymptotic notation expressions in your mind, you will have, oh, those are the sets in math. Yes. Yeah. So you will have a little better understanding. Yeah. If it is a set, we can use properties of set when necessary, right? Later, yeah, when we try to understand the working details, we may need to use the properties of set. All right? Yeah. I will explain. When we go there, I will explain what kind of properties we need for a set concept. That's discrete math. All right? This class, in the prerequisite, we have Math 3000. That's a big prerequisite for this class. Discrete math. I will use a lot of knowledge from discrete math. Okay? So this is one set concept. And this is one. Yeah. All right. Next.